Chapter 2.3, Venn diagrams and set operations. So in this chapter, we're going to be looking at using our understanding of what a set is to relate sets to each other. So as a review, remember that the universal set, which we symbolize as U, is the set that contains all the elements of any specific discussion. So remember, I used the example of if we're talking about animals and I ask you what can fly and you tell me airplane, that's not very helpful, right? So we're going to need to know that definition in order to talk about Venn diagrams. But what is a Venn diagram? A Venn diagram is a useful technique for illustrating set relationships. So the Venn diagram was invented by John Venn, who used them to illustrate ideas in his works on symbolic logic, which is something we're going to learn a lot more about a little bit later. So to create a Venn diagram, we start with a rectangular frame. This rectangle is used to represent the universal set U. We will often define U somewhere in either verbally or just write it out. U equals animals up here. Like maybe we'll just say animals so that we know that that's what we're talking about. But for right now, I'm just going to work symbolically, so I'm going to call it U. Then the items inside the rectangle can be divided into subsets of U. Each subset is represented by a circle. We would then label the circle. Here I'm labeling it with the letter A, but I might label it with a verbal description or whatever notation I'd like to use here. Now, taking all of that into account, we get different ways we can organize these subsets depending on how they're related to each other. So the first possible orientation that we can run into are called disjoint sets. So two sets which have no elements in common are said to be disjoint. So here I have A and B. I've drawn them as non-overlapping circles because they do not overlap. They have no elements in common. So, for example, 3, 4, 5, and 7, 8 would be disjoint. If I have A is 3, 4, 5, I can write those three elements in A. I can write 7, 8 in B, and we can see that they have no overlap between them. So we often say this means that their intersection is the empty set. Now, intersection is something we're going to get into a little bit later. How do I denote proper subsets? Well, a set A is a proper subset of set B. If a set A is a proper subset of set B, then all elements of set A are inside set B, but B has more elements, right? So we can draw this as A is inside of B, but B is larger. But if instead we have a subset where they're actually just equal to each other, then we would draw them as the same circle and label it as both A and B. So these would be the same set. Whether we said A equals 1, 2, 3, B equals 3, 2, 1, they're the same set, right? So this would still just be 1, 2, 3, right? Because these elements are just sort of floating in space. It doesn't matter where I write them, so these are the same set. Now, when I have two overlapping sets, this means two sets who have some but not necessarily all elements in common. They have overlap. So we draw the sets as overlapping, but neither is directly inside the other. So this is the most general form of a Venn diagram because we can actually represent all cases using this format. So if you don't know automatically which of the previous formats something falls into, if it does at all, then this is the format you would want to draw your Venn diagram with to begin. So looking at the general Venn diagram, here I have numbered each of the parts of the Venn diagram, 1, 2, 3, and 4, or the regions. So to illustrate disjoint sets, where there are no elements in common, then we would just have something is in region 1, something is in region 3, but nothing is in region 2. That's what no elements in common means. To illustrate subsets, if A is a subset of B, then we would have nothing in region 1. But if B is a subset of A, then we would have nothing in region 3, because we can see that that means they have stuff in their overlap, but nothing outside. So that would mean they are subsets. To denote equal sets, all elements would simply be in common. The area in common is the overlap. So region 2 would have all the elements of A and B, nothing would be in 1 or 3. And finally, just normal overlapping sets. We get elements in A but not in B would go in region 1, elements in common between A and B would go in region 2, and elements in B but not in A go in region 3. But what about region 4? So in each of the 4 cases, any element belonging to the universal set but not to either set A or set B is placed outside of them in region 4. So let's say we go back to the example of U being animals. And A is maybe things that fly, and B is things that lay eggs, right? So here's fly, here's lay eggs, we're talking about animals. So some things that could go in each of these areas would be something that flies and lays eggs could be a robin, right? That's in their overlap. Something that lays eggs but does not fly could be a fish. Something that flies but does not lay eggs would be a bat. And then something that's in neither of those, it doesn't fly, it doesn't lay eggs, could be like a cat. So that's how we could fill this out, right? And there are plenty of other elements that can go in each of these areas, but this is just an example of one thing that could help fill out this example. Now it's time to talk about set operations. So we can use the notation for sets when we're using the capital letter notation to sort of do operations in the same way we do with numbers. We can do addition and subtraction and stuff like that on numbers. Here we're going to start by using what is called the complement. So the complement of a set A, which we will symbolize as A with a little apostrophe up in the corner, is the set of all elements in the universal set that are not in set A. So this sort of takes A and what's called inverts it. It's everything not in A. So often we will even read the complement as just not A. So if we wanted to find a complement and make a Venn diagram for the universal set of A, B, C, D, E, F, G, and A as A, C, E, I have 2 ways to do this. I can start from the Venn diagram or I can start from the complement. If I start from the complement, all I have to do to get a complement is go through and cross out A, C, and E. A complement is whatever is left over. So I can know my answer pretty quickly. B, D, F, and G. But if I'm drawing the Venn diagram first, I would put in each of these elements, A, C, E, are going right in the middle in A, and everything else that I haven't placed already go elsewhere, go outside of A. And so A complement is just the colored in region, which is the area outside of A. So either way, we end up with B, D, F, G. So you can go in whichever order makes the most sense to you. Our next operation is called the intersection. So remember I talked about the intersection when I talked about disjoint sets, that disjoint sets have no intersection. Their intersection is the empty set. But in general, an intersection can be symbolized by what looks kind of like an upside down U, right? So A with this intersection symbol, this is read as A intersects B, is the set containing all elements that are common to both set A and B. So it's this area right here, it's region 2. So if I have U is the numbers 1 through 10, A is 1, 2, 3, 8, B is 1, 3, 6, 7, 8, and C is the empty set, how do I find their intersections? Well, once again, I can do this using just what is written here, or I can create the diagram to make my life a little bit easier. So, if I create the diagram, I start by placing each of my numbers within A and B and C. And then whatever's left over goes outside. So in this case, C is the empty set. It's sort of, I'm just going to denote it over here in the corner. It doesn't really matter where I put the empty set because it is empty. Next, I want to look at A. I'm going to start writing out the numbers of A, but I need to make sure whether or not there are things in common. So look at A and B. A and B have 1 in common, they have 3 in common, and they have 8 in common. So in fact, the only thing not in common is 2. Then 1, 3, and 8 go in here, and what's left over in B are 6 and 7. Then I go back to U. I once again notice that C just isn't going to have anything in it since it's empty, and I mark off anything that I haven't mentioned. So 1, 2, 3, 8, 6, 7. So what's left over is 4, 5, 9, and 10. And so I get the following. So if I want to then find the actual intersections, the intersection between A and B is just this area, right? So it's 1, 3, and 8. The intersection between A and C, well, there's no intersection. They're disjoint. But, of course, I could have drawn C here because it's the empty set. It doesn't matter where I put it. There is nothing to intersect because there is nothing in C. So this is kind of not really a trick question, but it's a question that always has the same answer. A complement intersect B. Now that's an interesting one. So the complement of A, we're going to color this in. So the complement of A is everything outside of A, right? And then B is everything in B. So what part of this did I color in twice? That's the 7 and the 6. So essentially, when I want A complement intersect B, I'm looking for whatever's in B that wasn't in A. So that's 6, 7. Now here, notice the parentheses. They matter. I take A intersect B and find the complement of that. So I start from here's A intersect B. The complement of that is everything outside of that, like so. So it's everything except 1, 3, 8, including the stuff that's out here in the universal set, of course. So that's all numbers between 1 and 10 except 1, 3, and 8 right there. Now you may be wondering, well, what if I had done A complement intersect B complement? Isn't that the same thing? And the answer is no, it's not the same thing. A complement intersect B complement would look like the following. So here's A complement, and then B complement looks like this, right? But ends up being, well, what did I color in twice? I didn't color in this area twice, I didn't color in this area twice, and I didn't color in this area at all. So it's only the stuff outside. So it's different. We will explore that principle a little bit later. It has to do with a thing called De Morgan's law. So that's something that we will talk about at the end. But the next operation is called the union. So the union is sort of the opposite of the intersection. The union of sets A and B symbolized by A and then what kind of looks like a U, but notice that we use the U for the universal set. That's actually a letter U. This is a union symbol. It is different than that U. Because of the way I write my U's, they tend to look very similar if I'm writing them by hand. But just please don't write it with a tail. It's not an actual U. It has its own symbol. So the union is all the elements in sets A or set B, or both set A and set B. So to think about the union versus the intersection, the intersection is where the sets intersect, right? So the sets intersect in the middle, right? It's where they cross over. Think about an intersection of two roads, right? Where they cross and there's a red light or whatever. We have an intersection. That's where the roads are crossing. This is where the sets are crossing. Whereas the union It's where the sets unite. So it's I have one set of things and another set of things, and I unite them together. So like the United States, or like if we had two teams that are coming together to make one big team, right? That's what's happening here. If I have, some pile of stuff and another pile of stuff, and I put them all into one big pile, it's now one big set, right? That's what's happening when we unite. And to, try to remember which symbol is which, U for union should be easy to remember, right? U for union. The other one, which looks like an upside down U, it looks kind of like a rounded N, and so I always think of it as like the intersection. But there is, of course, an N in union as well, so it's not the most helpful mnemonic. Okay, so here we have same sets as before, where U is the numbers between 1 and 10, A is 1, 2, 3, 8, B is 1, 3, 6, 7, 8. So can create same sets as before. I'm not going to go through that again. But now how do I answer the question of what is A union B, A complement union B, A union C, and A union B complement? So A union B is, of course, the thing that was colored in before. That's this whole area, because it's I take A, I take B, I put them all together. That includes the part that's intersecting. That's fine. So it's everything here. That's the union. Then A complement union B is taking the complement, so that's everything that's outside of A. So that's not how a circle is drawn, but it's all of that. And I'm unioning it with B. Well, B already has the 7 and 6, but B also includes this part. So it's everything except the number 2. Then A union C, well, C is the empty set, so I'm not really adding anything. But if I just take, I have a deck of cards and I have an empty deck of cards, right? I have that box that's empty and I plop them all onto one table. I still have the original deck of cards. It didn't go away. Nothing changed there. So that first deck of cards, I just didn't add anything. Okay? So A union C just ends up being what A was. And then A union B complement, once again, I have to do the union first. So A union B is all of this. Taking the complement of it, it's I go outside to get 4, 5, 9, and 10. And if, again, you're asking, well, what about if I had taken A complement, union B complement? Again, this is very related to that thing I mentioned before of De Morgan's law. It ends up being different, and we will explore that further soon. But just understand that A complement is everything outside, right? B complement is everything outside of B. Unioning them really just leaves off their intersection. It's a little bit different. Now, you'll notice that the way I've described the union and the intersection, I was very careful about using the words and or. Because the words and or have what's called a logical definition to them. They have a meaning that's very explicit, especially when we talk about sets, but when we get to our logic chapter, it'll be even more important, knowing the difference. So the word and is generally interpreted to mean an intersection. That is, if an element is in sets A and B, then we would say it is in the intersection of A and B. Because it is in set A, it is in set B. And, right? Set A and in set B. So we could write in set builder notation A intersect B as the set of all x such that x is in A and x is in B. But the flip side of that is the word or is generally interpreted to mean a union. That is, if an element is in set A or set B, then it is in the union of A and B. So A union B is the set of all x such that x is in A or x is in B. Now, we will get into, when we talk about logic, the difference between what is called the exclusive and the inclusive or. In this case, essentially, if you're wondering, we are including things that are within both. So their intersection, that's in A, B, or both, we include that, we just aren't saying it. Now, we've talked about cardinality of sets before. How is that cardinality affected when we talk about the cardinality of intersections or unions? So we can find the cardinality of a union. This is sort of the only one we're going to talk about explicitly, but you'll see the cardinality of the intersection is sort of part of it. To find the number of elements in the union of two sets, A and B, we add the number of elements in sets A and B, then subtract the number of elements common to both sets. So number of elements in A, number of elements in B, then remove whatever we would have double counted. So this formula only applies to finite sets. We're not going to talk about infinite sets here, but you're not going to see an example of it, so it's not going to matter. But why is it like that? So you have to think about the fact that we're talking about, we have some stuff in here, but when I count cardinality of A, then I'm counting all of this. Then when I count the cardinality of B, I'm counting all of this. So I've counted this part twice. It gets colored in twice, right? So if this is A and this is B, then the cardinality of A counts all of that. Cardinality of B counts all of that. So I have to subtract this one off one time because I've counted it twice. So it's, if this is X, this is Y, and this is Z, then I have X plus Y for the first guy, plus Y plus Z for the second one, which currently is X plus 2Y plus Z, right? So I've double counted the middle. So I subtract off Y by subtracting off the intersection to get rid of that 2Y and make it 1Y. Okay, so that's how we count the cardinality of our union. Now let's look at an example of this. The results of a survey of visitors at the Grand Canyon showed that 25 speak Spanish, 14 speak French, and 4 speak both Spanish and French. How many total speak Spanish or French? So again, pay attention to the ands versus the ors. So Spanish or French means one or the other or both. That's the union. So we want to know the union. We were given the intersection, that's the and, as well as the individuals. So if I say S is the set of visitors who speak Spanish, F is the visitors who speak French, then we would say the cardinality of S is 25 and the cardinality of F is 14, and the cardinality of their intersection is the 4. So then it's a matter of just plugging into this formula, right? I've replaced all my A's with S's, my B's with F's. Plugging into the formula, I have each of the numbers, 25, 14, and 4, to place into these positions. So 25 plus 14 minus 4 equals 35. And so that would say that there are 35 total people who were surveyed who speak these languages. The last of our operations that we're going to talk about is called the difference of two sets. So this one actually uses a symbol you'll be used to seeing. It's a subtraction symbol. So the difference of two sets, A minus B, is a set of elements that belong to set A but not to set B. So in set builder notation, we would write this as the set of all x such that x is in A and x is not in B. And we can see that it is sort of this area where we have removed the intersection, right? So essentially it's you're taking A and then anything that would be in B, we take it out. We remove it. We give it to B. We don't care about it. But remember that, for example, here I'm using letters. There is no actual subtraction that's occurring. So if I had numbers here, I wouldn't subtract the numbers. It doesn't mean we take, if this was the set 1, 2, 3, and I wanted to subtract the set 1, 5, 7, that I would subtract 1 minus 5 and 2 no. It doesn't work that way. It wouldn't work that way. How would we line them up? How would we know what's getting subtracted? That's not what we're doing. We would just remove the number 1 from what I wrote. So, here we have A is B, D, E, F, G, H, B is A, B, D, H, I, C is B, E, G, and U is the letters between A and K. So in this case, we actually have a three-part set where none of the sets are the empty set. So we're going to be introduced to a three-part diagram. We're going to explore three-part diagrams a lot more a little bit later. But for right now, just realize that all we're really doing is we're placing these elements and then putting a circle around them, right? That's all that's happening. So I'm going to place these three circles now, and I'm going to put each element where it should fall. So B is in A and B is in B, so B would go in their intersection. And D is in A and D is in B, so that's in their intersection. And, well, B is also in C, though, right? So it's in this intersection of all three, which means it would be here. And so if we follow through this, we get F is only in A, C, and I are, or A and I don't know why that C is there. That's a mistake. That should go out here. Sorry about that. But A and I are only in B, and J and K and C are outside. They're only in U. And then C doesn't have anything to itself because E and G and B are all in A, and B is also in B, and so we can see how this all lines up. Again, apologies for that little mistake here. We're gonna cross that out and just write it over here. There we go. So, given that, if I want to find A minus B, I'd be taking everything that's in A, but I want to realize that it doesn't matter whether it's in C. It's still in A. So everything that's in A is everything in this blue circle. And then I remove anything that's in the overlap with B. So this stuff is going away. So these three elements are in A minus B. Next, A minus C, I'd do the opposite, where I would cross out my B, G, E and keep my D and H. So another way we can see this, if we didn't want to draw the diagram or you didn't like visualizing it that way, is we can look at A and we just go B, E, G, I look for them, I cross them out, and this is what's left over. This, D, F, H, is A minus C. And then A complement minus B, once again, here I have to think about what is A complement. Well, if I take everything outside of A, so that's these guys, and then I want to remove B from it, well, these are the ones that are in B, so I'm just left with this, right? J, K, and C. And finally, A minus C complement. I need to know what C complement is. Well, C complement is everything outside of C. So everything outside of C is all of this stuff, right? But A minus all of that stuff would be left with this area right here, E, G, and B, like so. Again, that C should be in there. And there we have it. So the last of our, that's the last of our normal set operations, but there is one last thing we can do to sets to relate them. It's called the Cartesian product. So the Cartesian product is taking two sets. We can't visualize this using a Venn diagram anymore. We're going to symbolize it using A with the sort of times symbol. It has to be this specific times symbol, though. I know we can write multiplication symbol in a lot of ways. This is the one that is the cross, because we often read it as A cross B. It is a set of all possible ordered pairs of the form AB, where A is in A and B is in B. So we're creating a new set where we select first an element of A and then form an ordered pair with an element of B. And we do this as many times as we can to get every possible ordered pair there is. So if I have A is orange, banana, apple, and B is 1, 2, I start by, for A cross B, I take an element of A and an element of B, put them together as an ordered pair. So it'll be orange, comma 1. And so that's the first element of my set. So this is this. Then I'll take orange, comma 2, because I pair it with the next element. Then I pair, well, there is no next element in B, so I go on to the next element of A. Banana 1, banana 2. Apple 1, apple 2, like so. If I do B cross A, it matters which comes first here. So B, I start with 1 orange, 1 banana, 1 apple, 2 orange, 2 banana, 2 apple. But we can also do the Cartesian product of a set with itself. So A cross A becomes orange with orange, orange with banana, orange with apple. Banana with orange, banana with banana, banana with apple. Apple with orange, apple with banana, apple with apple. Taking these two sets and we're just making pairs the same way you would if you were graphing. So essentially, the way a graph works, where this name Cartesian product comes from, you may have heard the word Cartesian when you first learned about graphing, because when you graph on a set of axes, right, we've got our grid and all of that, blah, 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 right? This is often referred to as the Cartesian plane, same Cartesian, right? Because the Cartesian plane is made up of a Cartesian product of the real numbers with the real numbers. So it all kind of comes together. We're not going to talk a lot about that. Mostly you just need to know how to do the Cartesian product of a small set with another small set. How do you pair each of these things? But know that this isn't just a completely foreign thing to you. You've seen ordered pairs before. We're just now minimizing it to finite sets so it looks a little bit different.